Hello. In the previous lecture, we proved many results about splitting fields. Let me quickly recall what we proved about splitting fields. First of all, we showed that for every polynomial f with coefficients inside the field capital F, we do have a splitting field. What does that mean? That means that we can find a field extension E that contains elements alpha 1 dot alpha n that are degree 1 factors of this polynomial f, which means f can be written as product of these degree 1 factors, and E is the smallest field that contains these zeros, meaning if I start with capital F and add the zeros alpha 1 dot alpha n, I'm gonna get the entire field capital E. In that case, we call it a splitting field of the polynomial f over the base field capital F. And we showed the existence of such a field extension. Next, we showed the uniqueness of this field extension. What does that mean? If I give you any field f and a polynomial that's not a constant with coefficients inside this field f, if I tell you that E and E prime, both of them are splitting fields of this polynomial, then we can deduce with this polynomial over this base field capital F, then we can deduce that these two fields are isomorphic. Not only they are isomorphic, but also we can find this isomorphism in a way that it is F linear, it is identity over the field F. The proof of the uniqueness was based on a stronger statement that we can refer to as isomorphism extension. So what is the isomorphism extension theorem? It says that if I give you two copies of the same field through the isomorphism theta, and I give you a polynomial inside the first field, I tell you E is a splitting field of this polynomial over the base field capital F, and E prime is a splitting field of the copy of F in the other field, theta of F, then I can find some isomorphism between these splitting fields that's an extension of the isomorphism between F and F prime. And we can capture this statement in this commutative diagram, saying that if I give you an isomorphism from F to F prime, then if I consider embedding of F into the splitting field of this polynomial small f, and embedding of F prime in the splitting field of the theta of F, then I can extend this isomorphism theta to an isomorphism between these splitting fields, and we denoted this by theta hat. So essentially, this statement about isomorphism extension can be captured in this commutative diagram. Okay, and the proof of this isomorphism extension was based on the case where the polynomial is irreducible, in which case we can have a stronger statement and say that a zero of this polynomial can go to another zero via some isomorphism. So again, what is the precise statement? Suppose I give you an isomorphism between the fields f and f prime. Essentially, I'm giving you the same field, or two copies of the same field. I give you an irreducible element, irreducible polynomial with coefficients inside this field, f. I tell you that E is some field extension of f, and E prime is some field extension of f prime. I tell you that alpha is some element in the first field extension that's a zero of the polynomial f, and alpha prime is a zero of theta of f. In that case, the field f bracket alpha is indeed isomorphic to the field f prime bracket alpha prime. Moreover, I can find some isomorphism that's a field that's an extension of theta, which means it is compatible with theta if I feed it an element inside the field f, and theta hat sends the first 0 alpha to the next 0 alpha prime. This type of result we had used for quadratic equations, or at least pointed out in quadratic equations towards the beginning of the course. Now we have this vast generalization of that phenomenon. Okay, so these were the results that we proved about the splitting field. Now what we want to do today is to use these results to understand finite fields. Okay, so let's start with a finite field and see what we can say about it. Suppose f is a finite field. Then definitely its characteristic is a prime number. It cannot be 0, because if it's of characteristic 0, then I have a copy of ring of integers inside this ring, but f is a finite field. So definitely it has finite characteristic. But because it's a field, then its characteristic should be a prime number. So say the characteristic of this field is prime number p. The first thing that I'm going to claim is that order of a finite field of characteristic p is definitely a power of p. Okay, so let's see how to prove this. We have seen this type of argument earlier in some of the questions in the discussion and problem session. Let's go through the proof. Suppose L is a prime factor of the cardinality of the order of this field F. Then, by Cauchy's theorem from group theory, we do know that if a prime number divides cardinality of a finite group, then I can find some element that has that order. So this means if I consider the additive structure of this field, which is an abelian group, because L is a prime factor of the cardinality of this abelian group, I can find some element inside this field that has additive order equal to L. So it has an additive order equals to L. But what does characteristic mean? Let's try to recall that. Characteristic means that it is the smallest number that whenever I multiply it by any element of the ring, I end up getting 0. Because characteristic of this field is p, p times a should be also 0. But knowing that p times a equals to 0, I can deduce that the additive order of a should divide p. So that means L should divide p. But p is prime number. So L dividing p implies that L is p. So we just showed that the only prime factor of the order of f is p. That means the order of f is a power of p. And that's exactly what we wanted to show. So again, the only prime factor of this is p. And from here, I can deduce that the cardinality or the order of this finite field is definitely a power of p. Okay. Next, we want to understand the structure of f better, and we kind of follow what we had for z sub p. In z sub p, we had Fermat's Little theorem, which says that every element of z sub p has this property that when I raise it to power p, I get the element itself. A to power p is a in z sub p. Now, we want to say that in a finite field of order p to the n, every element raised to power p to the n is a. Okay, let's see how to prove this. If a is 0, then I'm done, because 0 to power anything is 0. Now, suppose a is not 0, then it's a unit inside this field. Now I can use the result from group theory that says that if I give you a finite group G, then every element inside this group, when I raise it to the cardinality or the order of the group, I get the neutral element. Now I'm going to use this for the group of units of this finite field. So therefore, every non-zero element of this finite field, when I raise it to the cardinality of the number of units, I end up getting 1. But the number of units is p to the n minus 1 because f is a field. So everything minus 0 gives me the units of this finite field. So a to power p to the n minus 1 is 1. Now we multiply both sides by a, and we end up getting the desired equation. So a to power p to the n is a. So altogether, we are showing this equality is true for every element a inside this field. Now from here, I can deduce a result similar to what we had for z sub p bracket x. What is it? If f is a finite field of order p to the n, then the polynomial x to power p to the n minus x can be decomposed completely as a product of degree 1 factors in f bracket x. In fact, this is precisely equal to x minus alphas, as alpha ranges over the elements of this finite field f. But I have to consider these polynomials as polynomials inside f bracket x. Okay, let's see why this is the case. By this claim over here, I do know that every element of p to the of f is indeed a 0 of the polynomial x to power p to the n minus x. So every alpha inside this field is a 0 of this polynomial. Therefore, I can use the generalized factor theorem and deduce that x to power p to the n minus x is some polynomial times product of these degree 1 factors. Now I can compare degree of both sides. Degree of the left-hand side is p to the n. Degree of the right-hand side is degree of q plus the number of terms that we have over here. But the number of terms over here is the cardinality of f, which is p to the n. So that implies that this q should be a non-zero constant. So q should have degree 0, which means it should be a non-zero constant. Now, if I compare the leading coefficients, I see that the leading coefficient of the left-hand side is 1. Therefore, this non-zero constant c should be 1 as well, which means I deduce the claim that x to power p to the n minus x is indeed product of x minus alphas, as alpha ranges over the elements of this finite field of order p to the n. Okay, so this means what? This implies that if I tell you f is a finite field of order p to the n, then f is a splitting field of x to power p to the n minus x over the base field z sub p. In particular, up to an isomorphism, there is at most one finite field of order p to the n. Again, let's understand the logic for the second part. If I tell you that f1 and f2, or f and f prime, both of them are fields, and both of them have cardinality p to the n, then if the first part holds, I can deduce that both f and f prime are splitting fields of the same polynomial x to power p to the n minus x over z sub p. Now the uniqueness of a splitting fields come to our rescue and shows that now by the uniqueness of splitting fields, I can deduce that they are isomorphic. So that's the in particular part. That is why it's enough to argue why a finite field of order p to the n is a splitting field of the polynomial x to power p to the n minus x over z sub p. Okay, so let's see why this is the case. Again, let me emphasize, if f is a finite field of order p to the n, then the claim is that it is a splitting field of x to power p to the n minus x over the base field z sub p. So the first thing that I have to argue is why it contains z sub p at all. So because the cardinality is p to the n, and characteristic of a field, a finite field, is always a prime, and it should divide the cardinality of the group, additive group, which is p to the n. So characteristic should divide p to the n, but it is also prime, so we deduce that it is p. Characteristic of a field is p, that means z sub p is the subfield. Okay, that's good. So we do have z sub p as a subfield of this field. Now, by the previous theorem, we know that x to power p to the n minus x can be written as product of degree 1 factors with elements inside this field f. That means what? That means when I add these zeros, which are these alphas, to z sub p, I get the entire f. So that again, that means f is the smallest subfield of f, which contains all the zeros of x to power p to the n minus x. Again, because if I give you all these zeros, then I'm giving you the entire f. That means that this f is indeed the a splitting field of x to power p to the n minus x. So that's what we wanted to show. We wanted to show that if a field of order p to the n is a splitting field of the polynomial x to power p to the n minus x over the base field z sub p. Now, if f and f prime, both of them are finite fields of order p to the n, then both of them are splitting fields of the polynomial x to power p to the n minus x over the field z sub p. Therefore, I can use the uniqueness and deduce that there is an isomorphism between these splitting fields. And that's exactly what we wanted to show. That shows the uniqueness of a finite field of order p to the n. But we haven't argued, we haven't showed that there is a finite field of order p to the n. What we showed is that if there is such a field, then it should be the splitting field of the polynomial x to power p to the n minus x over the base field z sub p. But this insight gives us a very good candidate for such a field. So next, what we want to show is that indeed a splitting field of the polynomial x to power p to the n minus x over the base field z sub p is a finite field of order p to the n. This is what we want to show. Okay, so let's start with such a splitting field. So suppose E is a splitting field of this polynomial over z sub p. Now we are going to consider all the zeros of this polynomial inside E. Notice that, again, if E was of order p to the n, we have already showed that all the elements of such a field should be zeros of x to power p to the n minus x. So that's an indication why we should focus on zeros of this polynomial. So let f be the set of all the zeros of this polynomial inside the splitting field of this polynomial. So that means I'm looking at all the alphas inside this set E, where alpha to power p to the n is alpha. So what we want to show first is that f is indeed a subfield. And therefore, f is the splitting field. F is E, but the equality between F and E we deduce later in an indirect way. Here I just argue why F is a subfield. In order to show F is a subfield, I have to show it is closed under multiplication, it is closed under addition, it is closed under negation. Every non-zero element is a unit. So these are the 4 steps that I'm going to take. Under multiplication is easier than the rest. So why is it closed under multiplication? Suppose I give you 2 elements, alpha and beta, inside this set. Then alpha, by definition, alpha and beta, both of them should satisfy these equations, which means alpha to power p to the n is alpha, and beta to power p to the n is beta. Now I want to say that it is closed under multiplication, so I'm going to consider alpha times beta, and I ask myself, what happens when I raise this guy to power p to power n? Because it's a commutative ring, it is the same as alpha raised to power this quantity times beta raised to power this quantity. But because of the equalities that we have over here, this one and this one, I can deduce this equation, and I get that it is alpha times beta. So alpha beta to power p to the n is alpha beta, which means alpha beta belongs to this set as well. Okay, so this shows that it is closed under multiplication. Why is it closed under addition? Remember, characteristic of this field E is P, is a prime number P. And in this scenario, we've seen that we can use, the freshman's wish comes true, meaning we do have a plus b to power p equals to a to the p plus b to the p for every a and b inside this field E. In fact, this is true for every unital commutative ring that has characteristic P. And the proof is rather easy. We just use binomial expansion, expand alpha a plus b to power p, and use the fact that p divides p choose I as long as I is in the range of 1 to p minus 1. So all these middle terms are actually 0 because the characteristic is p, so, and p divides all the coefficients. So all the terms in the middle are 0, therefore we end up getting only the last 2 terms, a to the p and b to the p, the initial term and the last term. Now if I raise both sides to power p, I end up getting that it is a plus b to power p squared, and on the other side I get a to power p plus b to power p raised to power p. But again, using the same equality, I get that it is a to power p squared plus b to power p squared. I can use this again and again, and I get that the same equality holds for every a and b and every positive integer m, that a plus b raised to power p to the m is a raised to power p to the m plus b raised to power p to the m. Okay, so now that we have this equality, we go back and try to show that f is closed under addition. So I give you 2 elements inside f, alpha and beta, then I consider alpha plus beta, and I raise it to power p to the n to see if I end up getting alpha plus beta. Because of the equality that we proved over here, I can write this as alpha raised to power p to the n plus beta to power p to the n. But alpha and beta are inside f, which means the first term is alpha and the second term is beta. So altogether, we ended up getting that alpha plus beta raised to power p to the n is alpha plus beta. And thus, by definition, implies that alpha plus beta is inside f, which means f is closed under addition. Now, why is it closed under negation? So you suppose alpha is inside f, which means alpha raised to power p to the n is alpha. Now you look at negative alpha raised to power p to the n. Negative alpha raised to power p to the n is negative 1 raised to power p to the n times alpha raised to power p to the n. I don't touch this for now, but this is alpha because alpha belongs to f. Now, negative 1 raised to power p to the n, if p is odd, that for sure is negative n. But when p is 2, remember p is a prime number. So if it's not odd, then it should be 2. Then the characteristic is 2, which means 1 and -1 are the same. So -1 to power p to the n is -1. Because it's 1, but 1 is the same as -1. So in either case, we end up getting that negative alpha to power p to the n is negative alpha, which means negative alpha belongs to the same set. Very good. Now, the last thing that we want to show is that every non-zero element is a unit inside this F. So I give you a non-zero element inside F. Because it's non-zero, it does have an inverse inside E, the field that we have, because E is a field, remember. And at the same time, alpha belongs to F, which means alpha to power p to the n is alpha. Now I am going to look at the multiplicative inverse of both sides of this equation. And I'm okay to look at inverse of both sides because we do know that alpha inverse exists. Now, alpha inverse is going to be inverse of alpha raised to power p to the n. But again, from group theory, we do know that it is the same as inverse of alpha raised to power p to the n. So we end up showing that alpha inverse raised to power p to the n is alpha inverse, which means alpha inverse is again inside this set, which means altogether we've showed that F is a field. Okay, so now we get to the critical point. We want to show that the cardinality of this field, this finite field, is precisely p to the n. So it takes us a few steps in order to prove this, but let's prepare the steps. What do we know about this set F? What was the assumption? How did we get to it? So we started with a splitting field of the polynomial x to power p to the n minus x over z sub p. What does that mean? This means inside this splitting field I can find alpha 1, alpha 2, alpha sub p to the n, and then decompose this polynomial completely into degree 1 factors. Remember, at this point I'm not assuming that these alpha i's are distinct. All we know, they might be all the same numbers, the same elements. But definitely there are these factors, degree 1 factors in this splitting field. And these alpha i's are all the zeros of x to power p to the n minus x. Remember, in an integral domain, a polynomial cannot have more than p to the n zeros, distinct zeros, and if I give you any other zero of this polynomial, you plug it in, and then on the left-hand side, you're supposed to get 0. That means it should be one of these alpha i's. So this consists of all possible zeros of this polynomial in E. So in order to show that the cardinalities, and remember the zeros of this polynomial gives us the set F. So that means from here I can deduce that this is precisely the set F. Remember, the set F is the set of all the zeros of this polynomial. So in order to show, so this is actually what I wrote over here, I didn't need to write it again. So that means that F is precisely the set alpha 1 dot alpha to the p to the n. So in order to show that the order of this finite field F is p to the n, I need to show that the polynomial x to power, I need to show alpha i's are distinct. Alternatively, we can say it's the same as saying that the polynomial x to power p to the n minus x does not have multiple zeros in the field E. So it does not have multiple zeros in the field E. Okay, so now here is a question. How can we find out whether or not a polynomial has multiple zeros in its field of fractions, in its splitting field? Okay, so that's a question that we want to understand. Do we have a mechanism to find out whether or not a given polynomial has multiple zeros in its splitting field? So this is what we want to answer. And we are going to use ideas from calculus. But remember, here we don't have limits, so we have to be cautious when we are using ideas from calculus. So from calculus, we do know that if we have multiple zeros, then that particular zero should be a zero of the derivative of the polynomial as well. Let's check the whole thing as well. But if you remember this from calculus, that's a good motivation in order to define derivatives of polynomials. And we are going to define them in a formal way. Because again, remember, we do not have limits and these kind of things for an arbitrary unital commutative ring. Okay, so what is the formal definition of derivatives? I give you a polynomial. And remember, we often prefer to not make a bound for the for n. We can write it I goes from 0 to infinity, a sub I x to power I. Then the derivative of this polynomial is nothing but I a sub I x to power I minus 1. And sometimes it is useful to write it in a way that the index doesn't start from 1 but rather 0. So sometimes we write it like this, that I goes from 0 to infinity, and then I have I plus 1, a sub I plus 1, x to power I. Sometimes it is useful to write it this way. Okay, so this is called the derivative of f, and let's see how it can help us. The key point is that even if we define this in this formal way, still the derivative of summation is summation of derivatives, and still we do have the product rule, meaning derivative of f times g is derivative of f times g plus f times derivative of g. So I leave this as an exercise for you guys to check and see why we have product rule. It's a bit messy, but it's not very complicated. So it's kind of a straightforward to check these equalities, but it's a bit lengthy. That's why I'm avoiding doing the computation. But let's see an immediate application of this product rule that's related to multiple roots. So suppose my polynomial f is x minus a squared times other polynomial. Then I say that implies that f prime at a is automatically 0. Let's see why this is the case. I use the product rule and I deduce that the derivative of f is derivative of the second one times the first term plus derivative of the first one times the second one. But derivative of x minus a squared is nothing but twice x minus a times g of x. As you can see, these two terms have an x minus a in common, so I can factor out this x minus a and I get this equality. In particular, I'm seeing that x minus a is a factor of f prime, which means f prime of a is 0, which means a is a 0 of f prime. So if I tell you a is a multiple 0 of f, I can deduce that a is a 0 of f prime. This is what this corollary tells me. Now we are going to show precisely when a polynomial has, or okay, does not have, or has. It depends if you want to write this sentence or it's contrapositive. So we want to pinpoint exactly when a polynomial does not have multiple zeros in its splitting field. Okay, so let's write down the statement. Suppose I give you a field f I give you a polynomial small f, and I tell you the field extension E is a splitting field of this polynomial over the base field capital F. Now, in this setting, this polynomial does not have multiple roots in its splitting field if and only if precisely when f and its derivative are coprime. So being coprime to its derivative is equivalent to saying that f does not have multiple zeros in E in its splitting field. Okay, let's prove this. This is an if and only if statement, so I need to show left to right and right to left. So suppose to the contrary that the GCD is not 1. That means I can find a non-constant monic polynomial Q which divides both f and f prime. Now remember, E is a splitting field of f, which means in E I can decompose f into linear factors. So that means I can find alpha 1 that alpha n inside E and write down f as its leading coefficient times x minus alpha 1, x minus alpha 2, x minus alpha n. But remember, this Q is supposed to be a divisor of f. And x minus alpha i's are irreducible inside E bracket x, and E bracket x is a unique factorization domain. That means that a divisor of f should be product of some of these irreducible factors. And especially because I assume it's monic, I don't need to multiply it by some scalar. So altogether I get that Q of x is x minus alpha I sub 1, alpha I sub 2, until alpha sub I sub k for some indices. And now, because Q of x also supposed to divide f prime, I get that, let's say, I sub 1 should x minus alpha sub I sub 1 is a factor of f prime, and therefore it's a zero of this polynomial as well. And remember, I mean, I can rearrange the indices and I can assume that this index is 1. There is nothing special about I sub 1. I can rearrange it and make it to be 1. So altogether, what we have deduced is that f prime at alpha 1 is actually 0. But I have product rule, and I know that my polynomial f is product of these degree 1 factors. So when I use the product rule, I have to look at the derivative of this multiplied by the rest. The derivative of the second factor multiplied by the rest, and so on. And because these are degree 1 factors, if you look at them, these are x minus alphas, and derivative of x minus alpha is just 1. It's like coefficient of x. Coefficient of x, these are monic degree 1 polynomials. So the derivative of all of these degree 1 factors are 1. So if I use the product rule, I end up getting that derivative of f prime, is of course its leading coefficient. That part is not very important. And then I use the product rule. The derivative of the first factor is 1, and I get the rest of the factors. The derivative of the second factor is 1, and I get the rest of the factors. The derivative of the third factor is 1, I get the rest of the factors, and so on. And the derivative of the nth term is 1, and I get the rest of the factors. Now, when I plug in alpha 1, what happens? When I plug in alpha 1, this guy is 0. So the second term in the summation disappears. Then again, you see in all of these terms, x minus alpha 1 appears, except the first term in this summation. So that means when I plug in alpha 1, the only term that resists is the first term, and that means I end up getting that f prime at alpha 1 is a times alpha 1 minus alpha 2 times alpha 1 minus alpha 3 times alpha 1 minus alpha n. Now, when I tell you f prime of alpha 1 is 0, I can deduce that one of these terms should be 0. So for some I, alpha 1 minus alpha I should be 0, which means f has multiple zeros in its splitting field, and that's exactly what we wanted to show. Now, let's go the other way around. Suppose that it does have multiple zeros inside its splitting field. So for some alpha, it is x minus alpha squared times gx. Then, as we showed in the previous lemma, corollary, using product rule, we can deduce that f prime of alpha is 0. Now notice, both f prime and f are polynomials inside f bracket x, and both of them have alpha as a 0, which means the minimal polynomial of alpha in f should divide both f prime and f. So from here, we deduce that the minimal polynomial should divide the greatest common divisor of f and f prime. In particular, this greatest common divisor cannot be 1. Okay, so we showed both sides. Very good. So now we have a very good understanding under what condition the polynomial does not have multiple zeros in its splitting field. So let's go back to the polynomial x to power p to the n minus x. So I want to say that this polynomial does not have multiple zeros in its splitting field over z sub p. By the previous proposition, it's enough to show that GCD of f and f prime is 1. So I need to find what is f prime, where f is this polynomial. F prime, by definition, is p to the n times x to power p to the n minus 1 minus x. But remember, characteristic is p, so p to the n is just 0, so I get negative 1. So f prime is just negative 1 in z sub p bracket x. And GCD of negative 1 and any other polynomial is just 1. And that shows that x to power p to the n minus x does not have multiple zeros in its splitting field over z sub p. That means this set of zeros has exactly p to the n elements in the splitting field of this polynomial over z sub p. Now let's summarize what we have proved. We showed the existence. We showed that if p is prime and n is a positive integer, then there is a finite field of order p to the n. We showed uniqueness. If f1 and f2 are two finite fields and they have the same cardinality, then they are isomorphic. And we show how we can construct it. If I give a finite field of order p to the n is precisely a splitting field of x to power p to the n minus x over z sub p. Now that it is unique, I can actually denote it by something. At least up to isomorphism, it is unique. And we denote such a field by this bold or blackboard font f, this bold f, sub p to the n. So this notation we are going to use for a finite field of order p to the n. So we will continue studying finite fields of order, finite fields further in the next lecture.